we will talk about we have talked about in chapter 9 the chain growth polymerization, particularly the radical polymerization reactions. Okay, in the radical polymerization reactions, or even the overall chain growth polymerization reactions, we need to know about the initiation, propagation, and the termination steps, and also finally the chain transfer the steps. In the non-radical addition polymerization reaction, which is the Ionic polymerizations, we also have initiation, propagation, and termination. But as I told you already, this Ionic polymerization is much more complicated than the radical polymerization itself, because we need to use the negatively charged ion and positively charged ion, and also in the presence of solvent and solvation power. Because if you have a negatively charged ion, in the case of anionic polymerization reactions, you should have a positively charged gegenanion or counter ion. Okay? And the solvent power, or the type of this gegenanion, or the power of this negatively charged ion, will determine the association power between the negatively charged ion and positively charged ion, and the dissociation power of these total ions. And it's much more complex. That's why it's much more complex than the rest of the radical polymerization reactions. So we will be able to look at what is the characterization of ionic polymerizations. What about the kinetics? How you determine the degree of polymerization, how you determine the molecular weight of your anionic polymerization and cationic polymerizations. What are the factors influencing the kinetics of polymerizations as well? So we will look at these in detail. First of all, we have we will look at the Staudian polymerization reactions, but let's think about the anionic polymerization reactions. Anionic polymerization reactions is the one that you have a negatively charged chain end. Okay, we call this as the carbanion because you have a carbon with the negatively charged ion is called the carbanion. Carbanion is formed with the initiator and the double bond containing material, such as styrene, such as vinyl, the monomer. Okay? But when you have an initiator should have a negatively charged ion at the end of your chain, at the end of your initiator, such as butyl lithium, butyl group, butyl lithium. Butyl will attack this one of the chain end, and you open this chain and will become the carbanion at the end of your chain. But there is a requirement of this reaction. You should have a negatively charged initiator, okay? Whereas all substituent group should be acting as an electron withdrawing group. Okay? If you pull the electrons from this double bond, okay, then this position, left-hand side position and the right-hand side position, is a little different in electron density. Okay, when you pull the electrons from alkyl or whatever, the al, then X, for example, then electron density of the left-hand side carbon is a little weaker than this one. Okay? This is much more electron rich than the left-hand side. That's why the initiator can attack this left-handed side rather than the right-handed side. Okay? That's why electron is moving, as you can see in the arrow. Okay? That's why it becomes negatively charged carbanion at the end of the chain, so that it will become something like this. And this carbanion will also attack this monomer from the left-hand side and the right-hand side will be a carbanion. Okay, I think this is the minus charged one, and so on. So it will become a polymer, and that's why this is the called the anionic polymerization reactions. But we should have again the R should be electron withdrawing group, such as halogen or vinyl group, or many of the other electron withdrawing or strong electron withdrawing groups, or something like this. Okay? So this is very similar to the Michael's reaction in your organic chemistry. Okay, the Michael's reaction, I think if you have looked at the McMurray's book in chapter 16, you can take a look at the Michael's addition reactions, and this is very similar to the vinyl addition. And nucleophile will attack this vinyl, one of the end of your vinyl, and the hydrogen will be attacked in the second monomer. So in this way, you can form the polymer. Okay, so initiation, propagation, and perhaps later on you will see the termination reactions of this polymerization reactions. Whereas in the case of cation polymerization, we should have an electron donating group in al, okay, such as alkyl group. If you have a methyl, then it's a weakly electron donating group. So the electron density of this vinyl group is a little richer, so that it will attack as something like a nucleophile. It will attack this initiator, which contains positively charged chain end, okay, in the initiator. So with this reaction, you form a positively charged chain end called carbocation, okay, and this way this reaction will be repeated to become a polymer. Okay. The basic difference between the anionic polymerization in the previous case and the cationic polymerization is the initiator. Type of the initiator is different, and type of your monomer is different in terms of the substituent groups. Okay? Right? Substituent group should be electron donating in the case of cationic polymerization, whereas in the anionic polymerization, you should have an electron donating group, electron withdrawing group, excuse me, electron withdrawing group, and the initiator is a negatively charged the initiator. So this way, we can differentiate the anionic polymerization and cationic polymerizations. Of course, the chain end is different. In the cationic polymerization, you should have a positive charge, whereas anionic polymerization, you should have a negative charge at the end of your chain. Okay? So in the general scheme, if you have anionic polymerization, we have initiation, propagation, and terminations. Okay? The initiation is the one that when you have a vinyl monomer, such as vinyl chloride, we have Bg. B is a base, and G is kind of a counter ion or Gegen ion. Okay? And base will attack this, the vinyl group, and you form the carbanion at the end of your chain, and you form a counter ion. The jet will become a counter ion. Okay? In this way, you add the monomer here, and you add you propagate to become a final polymer, and finally at the termination step, if you have a proton coming from some component, such as water, such as ethanol, or any proton donating group, then proton will terminate this carbanion, so that you have a final inactive species at the end of your chain. And this is the general scheme for initiation, propagation, and termination of your anionic polymerization reactions. If you take a look at very closely about the styrene polymerization reactions in the anionic polymerization way, we have an initiator. This is called the butyl lithium. Butyl lithium. Butyl lithium. Okay, butyl will act as a negatively charged ion, just like a carbanion. Okay? And lithium is a positively charged one, so that the carbanion will attack this, beta carbon, and the alpha carbon will become the carbanion again, so that in this way you have a carbanion in the alpha carbon, so that you propagate and terminate when you have a proton donating water into here. So this scheme is not correct, as you can see. 좀 잘못됐는데요. I think you should have something like this instead of covalent bonds. Okay? Instead of these covalent bonds, you should have negatively charged the carbanion, and lithium positively charged the lithium ions. And here too, you should have a negatively charged minus and plus instead of this covalent bonds. You should have a minus charged one here, and 선 없애야 돼. 이거 없애야 되나? 요즘 실수가 많은데. And so on. And finally, you have a terminated species. Okay, this way you have initiation, propagation, and termination of your the butyl lithium as an initiator and the styrene as a monomer, and you form the polystyrene with a high molecular weight in this case. And note that we have an initiating agent here, proton donating water. So in this styrene and butyl lithium system, the water, small amount of water, will terminate the polymerization reactions, so that the water should not be present in this polymerization systems. Okay? If you don't have any water here, there is no termination step. Okay? So at the end of a chain, you still have active species, anionic species still remain. And if you add monomer, then you will still proceed polymerization reactions, and by adding more, you have you have a repeated increase molecular weight of your components. So actually, without this water, what you can see in terms of the degree of polymerization is that if you add monomer, if you have a monomer, okay, for example, if you have 1 mole of initiator, okay, and you have 10 moles of the monomer, 10 moles of monomer, your degree of polymerization will be exactly about 10. Okay, so if you know the initiator concentration and the monomer concentration, you will be able to find the degree of polymerization, because there is no termination steps. Okay? If your purity of your monomer and purity of the initiator is exactly the same, without any terminating the agents. Okay? So the ideal ionic polymerization is the one that what we can see is living polymerizations. Living, because you still have a negatively charged carbanion if you don't have any water. Okay? If you are very careful and can control the polymerization systems, you have a living chain end, so that after 1 day or 2 days later, if you add the monomer again, and there is no polymerization step, if you are careful about this water. Okay? So this is why we call this as a living polymerizations. And if I read, negative centers repel one another, therefore the termination by recombination is not possible. Okay? So it's because you have a negatively charged and negatively charged chain ends, okay? Chain ends, it's not possible to combine together by the combination reactions or disproportionation reactions, just like what we have seen in the radical polymerization reactions. So your chain end is still negatively charged one, okay? And well, there is no way of terminating this polymerization without adding water, without adding proton donating groups. So if you don't have any water, this is the living polymerizations. Terminator, in this case, is water, okay, for example. So initiation is normally very fast relative to propagation, and all chains grow very simultaneously. This leads to polymers with low polydispersity or monodispersity. So you can make a monodisperse polymer, okay, or narrow molecular distribution of your polymer in anionic polymerization reactions of your polystyrene in this case. Theoretically, therefore, MW divided by Mn is 1 plus 1 of Xn. Okay? And if Xn is infinite, then it will be pretty, if Xn is large, then this will be 0. So MW divided by Mn is about 1, which means that you have a monodispersed polymer. Rate of polymerization for polymethyl methacrylate or polystyrene is very high, even at low temperature, which is minus 78 degrees C. Okay? So if you decrease the temperature, usually the polymerization rate is quite low, or vice versa. If you increase the temperature, reaction rate is very high in the case of radical polymerizations. But in this case, anionic polymerization rate is very high, even at minus 78 degrees C. And this is partly due to the high concentration of the anionic centers. Therefore, degree of polymerization, Xn bar, is equal to K. K is a constant. K could be 1 or 2, and I will explain why 1 or 2. But actually, this is the monomer concentration divided by the initiator concentration. Okay? Initially present, 0 is an initial cases. So if you have a 10 moles of a monomer and 1 mole of an initiator, your degree of polymerization will be about 10 in previous cases. Okay? So I will explain to you why there is a case for 2. Okay? So if you know the monomer concentration and initiator concentration, you can exactly control the degree of polymerization in the case of anionic polymerization reactions. Okay, let's take a look at the case. K is equal to 2 and K is equal to 1 cases. Let's take a look at the K is equal to 2 case. Okay? Now, when you have the polystyrene, okay, styrene is the same, but let's think about that we have an initiator system containing potassium as an initiator, okay, potassium, but in the presence of naphthalene. Okay? When you have naphthalene and potassium, what you will do is even at minus 78 degrees C, in the presence of THF, you will form a naphthalenide. Okay. And there is no way of expressing this, the radical over there. This one, will be something like this. What you can do is that potassium will donate the proton, so the naphthalene, one of this electron and one of this electron from 2 carbon will form the double bonds, but you have extra electron on top of this, and this is called negatively charged carbanion and radical. Okay, this is called the naphthalene. The radical anion. Okay. So you form the radical anion and the potassium, the carbocation, potassium as a counter ions. Okay, that means that you have an anion and radical present all the same in one naphthalene units containing the potassium. Okay, this radical anion will attack this monomer, and you form the one of this radical, one of this electron will be added to here. So you form the another radical anion here, and one of this radical anion, two of them will be gathering together to form the covalent bonds. Okay, covalent bonds. Okay, one of the radical will form the covalent bonds, but at the end of your chain, you still have the carbanion. Okay? So you have 2 carbanion at the end of your chain in the alpha carbons, and potassium will be the counter ion, the present as a counter ions. Of course, you still have a naphthalene, and naphthalene is regenerated, okay, because of this step. Now, they knew that the color changes from this reaction. Color changes from white to the little yellow or purple color, and will become again the no color. So they knew that the radical anion is formed and then regenerated again to naphthalene, and by changing this step, they knew that this is really the case. And they knew that this presence of this radical anion by knowing the ESL measurement, because ESL can detect the presence of radical, okay, and this has been already known. Now in this case, you have a two carbanion, okay. So therefore, molecular weight of the total will be doubled. That's why the K should be 2. Right? K should be 2. So in this way, polymerization is mostly done in the THF solvent. THF solvent. The THF is tetrahydrofuran. The boiling point is about 50 degrees C, so it's very volatile solvent. It's like an acetone, and it's very polar. So polymerization is mostly done in THF solvent, and not the solvents like cyclohexane or benzene, and this was not possible. So the degree of polymerization will be given by the 2 times the K is equal to the 2 cases, because we have two the monomer gathered together again, okay, as usual. This is what we call the electron transfer reaction. Okay? So electron transfer cases, K is equal to always 2. Whereas in the next case, just like what we have seen, okay, the butyllithium case, you add 1 initiator carbanion will attack this one monomer at THF minus 78 degrees C. You have one cases. Therefore, this is the case for the K is equal to 1. So the concentration of monomer and concentration of initiator will be determining your degree of polymerizations. In the case of butyl lithium or some other cases, you still have you can initiate the methyl methacrylate. The methyl methacrylate is can be of course make the carbanion, but this carbanion, the concentration of this carbanion or the strength of this carbanion is a little complicated because methyl group is electron donating, whereas this carbomethoxy group is electron withdrawing. So it's a little bit more complicated in the case. Anyway, this polymerization can be done in THF solvents and can be done in non-polar solvents as well in this case. So by the nucleophilic attack, the K is equal to 1, so that you know exactly what is the degree of polymerization by knowing initial concentration of your monomer and initial concentration of initiator. Right? So degree of polymerization will depend upon the M and I, M0 and I0, in the case where you do not have any terminating agent, right? Just like water. Now, we have limited cases where when you mix together the styrene monomer and methyl methacrylate together, okay, when the styrene monomer forms the negatively charged carbanion, and carbanion will act as an initiator, okay, you can attack the styrene, right? You can attack the styrene monomer and can form the polystyrenes. Well, what if we have a second monomer in the case of copolymerization reactions? When we have a styrenyl carbanion first and can attack the case of methyl methacrylate, you can attack this vinyl group and form carbocationic styrenyl and methyl methacrylate anions. But this monomer, this growing chain, although it has the negatively charged ion, cannot attack this styrene because the initiator chain end is a Lewis base, and the strength of this base is stronger than this one, okay, right? So that this is a little weaker to attack this monomer. Therefore, this second reaction is not possible. So if you have a styrene monomer and methyl methacrylate, you always form the polystyrene rather than copolymer of styrene and methyl methacrylate. But anyway, in this case as well, we can determine the degree of polymerization as M over I, M0 over I0. M in this case is the styrene, and I is the initiator butyl lithium in this case. So if I summarize the anion polymerization reactions, you have a covalent bond, a covalent bonded one, and you have ion pair. Ion pair is has an association power, but this association and dissociation power depended upon polarity of your the solvents and the strength of your negatively charged ion and the positively charged ions. So when you increase the solvent polarity, it becomes free ions finally, okay? Finally, so that you can it cannot this anion can attack this another monomer. That's why THF as a polar solvent can form the polymerization reactions. The Kp rate of polymerization will increase, or Kp polymerization rate constant will increase as you increase your solvent power and becomes a free ions. Polymer tacticity, however, will decrease. Okay? Tacticity means when you have a symbiotic, atactic, and isotactic polystyrenes are the examples of the tacticity, but tacticity is not the same as what we can see here. So polydispersity is low because the reason might be that the rate of interconversion between the different forms is much faster than the polymerization reactions. Anyway, this way you can form the very narrow molecular weight distribution of the anionic polymerization cases. Termination is can be done by many steps, okay? But the proton donating group will terminate this carbanion or anionic species at the end of the chain because if there is anything that can attack this proton, will terminate in this way, as you can see here. There is also a possibility of other cases, such as if you have a little bit of a CO2, you can form carboxylate anion. Carboxylate anion is a Lewis base as well, but it's not as strong as the the carbanion that was formed before, so that there is no power to attack this monomer. So this is regarded as a terminating step as well. You can have the 1,2-dibromomethane, but 1,2-dibromomethane will not be added, right? Will not be added, potentially, so that this is the case where you have a final polymerization termination steps. But most important case is the proton. Okay, proton. So in the next step, we can take a look at the proton donor. Proton donor will be the water. If there is a water, proton will attack this. Will be attacked by the carbanion. So you have a terminating agents. Okay. Of course, you still have a hydroxide, but hydroxide is not as a strong base as this carbanion. So there is no further reaction. And in this case, chain transfer coefficient of this water is very high. C transfer agent due to the solvent is about 10. Whereas if you have ethanol, you can still have a proton donating group to this carbanion, but this chain transfer agent is chain transfer constant is about the 4 orders of magnitude lower than the chain transfer constant of water. Of course, you form the ethoxide, but this ethoxide is no longer living. It doesn't attack the monomer, so there is no action for the ethoxide to become initiator. Anyway, this is the termination step, and you see chain transfer coefficient is very high for the water. So again, if you go back to the original anionic polymerization cases, the termination step is governed by the presence of water. So you should be very careful about the purification of your initiator and purification of your monomer. Okay? Monomer should not have any water. If you have a small amount of water, because of the very high chain transfer coefficient, it just stops the polymerization reactions in anionic polymerization reactions. If you are very careful, removing all the water in your reaction systems, including the initiator and the monomer, then your chain end will be live will be alive, so that we call this as a living polymerizations. Okay? Living polymerization is possible just in the case of where you do not have any water or any absence of impurities, okay? Absence of the water or ethanols. Termination step might be possible in some other cases as well, but it's not very typical. But you can think of some other cases. Okay? Proton is very, very important, but there might be a very small possibility, very small probability of termination steps that I will introduce to you. Okay. First case is hydride elimination case without any impurities. Hydride elimination is the one that you have a chain N with the carbanion, okay? But this will be a terminating just like this, and hydride is eliminated from the beta hydrogen, beta carbon and hydrogen. You eliminate the hydride H. Hydride, okay. Usually the hydrogen radical, hydrogen will have only one electrons, but if you have additional electrons, it's called the hydride. If you do not have any proton, if you do not have any electrons in hydrogen, it's called the protons. So hydride is eliminated, taking one electron more from this CH bond, okay, and you form the double bond because of the electron rich. The two electrons will form the double bonds, and this will be a terminating species. It's also possible that this chain end carbanion and the double bond containing polymer terminating spat will form this allylic anions. Allylic anions is the one that you have this is called the allylic components. This allylic component is very inactive because your carbon will form double bonds, right? And you have one more electrons. And one of these so if I will call this 1, 2, and 3 carbons, you form the double bond from between the 1 and 2 carbons, but the 2 and 3 carbon will form the double bonds, whereas one will become the radicals. So radical will be moving from 3 carbon to 1 carbon, and this is called the resonance stabilization. And because of the resonance stabilization of this allylic anion, instead of attacking the monomer, it just stays in the allylic anions. Therefore, the allylic anion is known to be a very inactive, very unreactive. Okay? And in this way, if you form this allylic anion, this is regarded as terminated components. anyway, if you look at the possibility of terminating steps, terminating agent will be water, terminating agent will be the ethanol, or terminated by the hydride elimination, eliminations in these cases. Finally, the termination could be done by the presence of the monomer, which is polar. Okay? In some cases, if you have the methacrylate and the butyl lithium may react with the monomer, which is polar monomer, and form some component like this. Okay, and you have a methoxy the lithium, and this methoxy lithium is not as reactive as this methyl lithium or butyl lithium, so that there is a chain transfer reaction, so that this monomer will be terminated cases. So therefore, the polar monomer should be very careful in the initiating these steps, we should choose the right monomer and the right initiators. Finally, backbiting or intramolecular reaction is also possible to be regarded as a terminating steps. Backbiting is the one that when you have a long chain, okay, when you have a long chain, this long chain, chain end will be a negatively charged one. But instead of attacking the monomer, the end of the chain, it will be folded to attack this, attack this main chain, something like this, okay? So that you form the cyclic components without any active sites, right? And this is what we call the backbiting. Backbiting is coming from the snake, right? The snake will attack the, his tail, so that the backbiting was coming from this direction. So this is one of the possibility. I mean, although it's written in a theoretical way, some people have identified and analyzed the carbonyl, the cyclic components, and this is one of the possibilities, although it's not a great chances. So they looked at the presence of a cyclic trimer by detecting the NML and IR and other techniques. They can identify the mechanism of this backbiting in the ionic polymerization reactions. So if you look at the one more time, we have a hydride elimination as a third termination mode, and there are some possibility of the formation of inactive species at the end of the chain by forming the terminating species or non-reactive allylic anions, which is unreactive, or we can have unreactive the monomeric species, such as this one, and something like this. And then finally, we can have a backbiting as a terminating mechanisms. We can take a look at the kinetics. Okay? Kinetics of polymerization in the case of anion polymerization reactions. But I think before we go further, I think I will just to stop, and we can take a look at what we have done so far.